Okay, so as Deep already said, the first 2 days we'll have this preparatory course, which is basically a crash course for the biologists to learn a little bit of maths and for non-biologists to learn a little bit of biology. So I should just explain, the idea is not to embarrass each other. Oh, you don't know what a derivative is. Oh, you don't know what a gene is. So please don't feel that, it's such a simple thing and we are spending 2 days on it, but it's just to refresh our memories. So I want some data first. How many of you didn't do any maths after 10th standard? It's okay. Okay. And how many of you didn't do any maths after 12th standard? That is, you did till 12th standard. You had some maths till 12th standard. Okay. 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 So what I'll do basically is to cover the appendix on basic maths from Bran and Deborah's book. So basically, it will tell you that, if I want to solve something, at least this much of maths I need to know. If you want to work out exercises or if you want to work out the boxes in the book, you need to know at least the maths given in the appendix of that book. So I'm just basically going to cover that. I will not go through derivations. I'll state most of the time the results, but if you want derivations, I'll happy to do that if time permits. Okay. So I'll just use the board. Have you taken down this? Shall I erase it? Okay. Okay. So it's extremely basic, but some of us might have forgotten it. So just let's recall things. So the first thing is basic calculus, which means differentiation and integration. So if I have some function of a variable x, निकाल दूं? So sometimes we denote the derivative of function by this prime. Okay, so I'll just give you this result. Suppose I have x to the power n. Its derivative is n times x to the power n minus 1, provided n is not equal to, oh no, it's okay. Okay, now I can also do second derivative. Which is e to the power ax. Derivative is, so the exponential, this is exponential function. Its property is the derivative gives you the function back up to some constant. So the derivative of e to the power ax is again e to the power ax with some constant. Second derivative will be is a square e to the power ax. Okay, this is just a list of things that I'm giving, which may be useful when you do more detailed things. What's the second derivative? What's the second derivative of sin x therefore? First derivative of sin x is cos x. First derivative of cos x is minus sin x. So therefore the second derivative of sin x is minus sin x. Okay. Log x, the derivative is 1 by x. And the second derivative, you can use this formula. Okay. Suppose I have some little bit complicated function, some combination of these things, let's say, and I want to take the derivative of this. So it's of the form sum of two functions. The derivative of this function is equal to f1 prime plus f2 prime. But f1 is a product of two functions, so we use what is known as a chain rule. So which says take the derivative of x to the power n, okay, keep the other one as it is, plus keep the first function as it is, and take the derivative of second function. Okay, so in general, if you have a product, you take the derivative of one of them, leave the rest as it is, plus second one you take derivative, leave the rest as it is. Is it clear? Okay, fine. Suppose I have some function like this. Okay, I'm plotting this function. It has some shape of this kind. So the first derivative, it has a meaning. It's a slope. Okay. So imagine I have some arbitrary function, some function of this shape. So what's the slope here? Is it a positive slope or negative slope? So slope, you know what the meaning is? Derivative is a slope at a point. What's the slope? Is it a positive slope or negative slope? Positive, right? It's increasing. And here, if I come in this direction, slope is negative. Slope is increasing, slope is decreasing. It was positive here, negative here. It must become 0 somewhere in between. So that point is this. It has a name. It's called a turning point. Okay. So these derivatives are useful to know where the function is maximum or minimum, and that's given as the derivative of function at that point becomes 0. The slope, I said the derivative is a slope. Slope was positive here, negative here. It must become 0 somewhere, and that point is the turning point. Okay. Second derivative, if it's positive, then that x naught is, what's the result? Is it a minimum or maximum? Minimum. And if it is negative, it's a maximum. Let's do an example. Please plot this function. I hope everybody has some notebook and a pen. Please plot this function for me. Tell me, how does it look? X is anything 0, is negative, positive, anything. Please plot this function. How will you plot this function? So when I plot a function, I look at its values at some simple few points. What's the value of this function at 0? 0. So 0, 0. Okay. Which other point do you think is a simple point for this function? 1, right? Because at x equal to 1, what is it? The value is 0. It's 0 again, right? Now, can you tell me what happens between 0 and 1? Can you plot this function? How does it look? Increases, decreases, increases, and then beyond 1, decreases, and here negative. Okay, you think something like this? Okay, now this is a special point at which it became maximum, and we just learned that we can find that point by looking at the derivatives. Can you tell me where is the maximum of this function? 1/2. Everybody agrees? No? Agree? Okay. So f prime x is 1 minus 2x using this result. Okay? Right? And I said, if I've set this equal to 0, that will give me x naught to be half. Right? I take another derivative. It's minus 2, which is negative, and therefore it's a maximum point. Okay? Okay, so one advice, general, not just biologists or physicists, everybody, when you have functions, please plot them. It's very useful. It helps you to remember, to see their shape. It's useful to do that. Okay? So this was something basic. Let's continue with derivatives a little bit more. So one thing that you will hear in many of the lectures is something called Taylor's series. I'll give you the result. So what this Taylor series tells you is, I want the value of the function at a point, but I also want to know in its neighborhood, in its vicinity, close to it. Okay, so Taylor series tells you, I don't want to go too far, just in the close by, can I simplify the function? So that helps you simplify the function and make approximations. So if I want, so let me first give you the answer. So I'm expanding, so I say that I'm expanding the function f of x in the neighborhood of x naught. Okay. So that answer is that f of x can be written as the value of the function at the point x naught. Okay. Suppose I don't want to go away from the point of expansion, the point where I want to be. So of course f of x will be f of x naught. That's this. Is it clear? So I have some function like that one. Okay. I want the value of the function in the neighborhood of x naught equal to half. So what is the value of the function at half? It's f of half, right? That's this. And I want to now go a little bit away from it, maybe this side or this side. Okay? In the neighborhood of it. So then I'm writing the series for that, which says that take the derivative and then calculate it at x naught. I'll give you examples. Okay, this continues for many functions, not all functions. Let me give you an example. So I'm just giving you the result. Let's just do some examples. Suppose I have function e to the power x. Okay, and I want to expand it at x naught equal to 0. Can you plug it in and tell me what you find? Plot the function exponential of x first. How does exponential of x look for positive x? How, like this? Does it go up and down? Does it go oscillate? It's oscillatory. How is it? How does it look? Exponential of x. Huh? Increasing function. At x equal to 0, the value is 1. Okay, right? That's how exponential of x looks. Right? Now, can you tell me? So this is the value of the function at 0, and I want to know just in the neighborhood, just this much. For some reason I'm interested in. I don't want to know all this stuff. Okay, so I have this very complicated equation which involves e to the power x. I don't need it. My parameters are such that x is small. It's in the neighborhood of 0. It is, let's say, 0.1 or so. It doesn't extend beyond 0.1. So I don't need a full complicated function. I just need something which is in the neighborhood of 0. So then I can use the series. Can you expand it and tell me? Please expand it quickly. Use that result. Use this and that. Tell me what's the series expansion of exponential of x. What's the first term? Huh? Louder. 1. And the next one? So 0 plus a, okay, I'm just using this notation, 1 plus a times something, 1. Next one, a square by, anything about it? No. Okay, so this is the series expansion for an exponential. 0 to infinity. It's an infinite series. Okay, it goes on. So in some applications, I don't want the whole thing. It may be useful to cut the series till here. That is, I'm approximating this function by this dot dot. Of course, this approximation is not good beyond a point, right? But if my region of interest is this much, I might as well work with just 1 plus a. Okay? So power series expansions of this sort, like the Taylor series, are useful, especially in approximations. Slightly a non-trivial example. Log of 1 plus x. Please plot and tell me the Taylor series expansion. Please plot this function, log of 1 plus x. What is the value of this function at x equal to 0? Huh? 0. And then, okay, and so tell me, how does it look? What's the shape of this function? Saturating at x equal to infinity. As x, no, but as x increases, it will keep increasing, no? It will not saturate. Is it always positive? It's always positive? How much is log of 1 by 2? Log of 1 by 2. Is it positive or negative? Negative. Remember, there's one property of log. Log of a by b is equal to log of a minus log of b. Right? That's ln 1 minus log 2. And this is equal to 0. You already told me that, right? So it becomes, it can be negative when the argument is less than 1. Okay? Now please plot. Okay, take it as a homework otherwise. Please plot this function and write down the Taylor series expansion. I'll give you the answer here. And like the exponential, oh, sorry, I didn't say what these things are. N factorial, should have said here. So this funny notation, n times this exclamation mark, it's called a factorial. It's n into 1 less of that, and so on till 1. What's the value of 3 factorial therefore? 6. Okay, so that's this notation. So unlike the exponential, log doesn't have factorials in it. All terms are coming with a positive sign, at least when x was positive. Here, signs are alternating. Okay, but I urge you to please plot the function of log. Okay, so this was about derivatives, and yeah, and it's also useful when you do some numerical stuff known as the Newton-Raphson method. So maybe I think I'm going a little bit slowly. Let me now come to integration. Okay so far? Yes? We need better. This thing is very dirty. Integration is like this. So, okay. So, if I have function f of x and I wrote the derivative of this, okay. So, derivative of x square was 2x. Integration is a reverse process, inverse process. So, integral of 2x dx is equal to x square. Okay. So, again, let me give you a list. So, integral of x to the power n, provided n is not equal to minus 1. Okay, why? Do you see why? Why did I put this condition n not equal to minus 1? Yeah, because I get denominator 0, right? Okay, So if n was minus 1, 1 by x, integral is log x. Remember, the last page we wrote, derivative of log x is, so integral of 1 by x is log x, okay? Integral is what will be the integral of sin x? Okay, sorry. Can you tell me the integral of sin x from what you just learned? What? Can't hear. Minus cos x. Okay? Okay. And similarly cos x. Right. What is the integral of log x? Integral of log x? It's not easy. Okay? It's a homework. Please work it out. I'll give you the answer. Please work it out at home. So this, what I just told you, I gave a function and I got a function back. Okay? These are called indefinite integrals. Then there are definite integrals in which when I integrate, I don't get the function back but a number. Okay? These are called definite integrals. So you will hear words like, okay, I'm doing this integration and from this limit to that limit. So those integrals are called definite integrals. From limit x0 to x1. Okay, so I'll get some answer as a number in terms of x1 and x0. And the interpretation of that is that if I had this function g of x, some arbitrary function, and from x0 to some value x1, this integral gives me the area under the curve. Okay, that's the meaning of this integral. An extremely simple example. Suppose my g of x was this, a constant b, and I wanted to do this integral. What will be the integral of this function? G of x is b, and it lies between 0 and a. Above that it's 0. Can you tell me the integral of this function? ab. But it's a rectangle, right? And that's the area of a rectangle. Okay, this is an extremely simple example of what I just said about area being the area of the under the curve being the definite integral. Okay, so this is just a little bit of calculus. Any questions? So basically, I think what you need to know is the Taylor series. That's important. You need to know what derivative is. At least some of them are very basic. You should just remember. Similarly for integrals. Okay. Okay. So now, let us do a little bit of linear algebra. So, vectors and matrices. Remember from school we used to represent a point like this by 2, 0. Everybody has done that, right? So we say we are specifying the coordinates of a point. How about this point? What will I write? Analog of this 0, 3, right? And this point 2, 3. Right? And if I put some funny things like arrows, okay? Okay, these are examples of vectors. So all these 2, 0, 0, 3, these are vectors when I have put some signs. Okay. So I will write two types of vectors, a row vector and a column vector, which I'll denote in the following manner. A row vector is a row that is, so I'll define a vector with n components. So this one has 2 components. This is a row vector. I'll write it in this manner. And a column vector it's a column. Okay, so instead of writing 2 0, I could have written 2 and 0 beneath it. Okay, matrix has both rows and columns. So an example, so this is a matrix. It has 2 rows, right, and 3 columns. So we call it a 2 by 3 matrix. Okay. Therefore, these row vectors and column vectors are also matrices, right? So this one, a row vector is a n cross 1 matrix, and a column vector is therefore 1 cross n matrix. Okay. So these, okay. So it also is a part of it. Okay. If the number of rows and columns are equal, we call it a square matrix. So many times we will wind up doing operations with square matrices. So it's a square matrix. Did you see my notation? I've been writing this A11. Oh, what does it mean? It means I stay in the first row, first column, first row, second column, first row, third column. Okay? So we frequently write it in this manner to specify where we are. Okay? So when I say 822, it means second row and second column. Okay? Okay. Now let's do a little bit beyond the definition. Let's take the product of matrices or product of matrix with a column vector or row vector. So let's take a 2 by, so this is a 2 by 2 matrix. And I want to take the product of this with a column vector. Now those who have done till 12th standard maths, please tell me the answer. So what is, the result is a matrix or is it a vector? And if a vector, what kind of vector? Column vector, row vector? Is it a vector, the product, if I, after I have taken a product? So this is a 2 by 2 matrix, and this is a 2 cross 1 matrix. You can take a product only if these two things are same. Okay? And the result is a 2 cross 1 matrix. 2 rows and 1 column. That is a column vector. How do we take this product? Multiply this row with this column. So just see the operation. A11 x1, okay, plus this guy with this guy. Okay, that's my first element of the resulting column vector. Then A21 with x1 plus this into this. This is my new column vector. I have multiplied the matrix and a column vector. Okay? Can I do this? Same A matrix. Does this operation make sense? No, right? Because this is 2 cross 2 and this is 1 cross 2. And I told you the rule, right? I can't do this, but I can do this. Okay? Please work it out yourself. How about 2 matrices? Can you do this? So use the similar rules that I told you just now, right? So think of it as a row vector, multiply this, and you will get this whole matrix with just this column. You will get one column. Then apply the same operation, the matrix on this column, and then you will get another column. So I'll give you the answer. So I multiply this with this, okay, plus this with this. That's the first element, A1. So if I call this matrix C, this is my C11, okay? Okay. So this I'm writing longhand, but the simple thing that you can remember, and it's easy to remember, is the following. So if I had a matrix C, just like I gave you for this example, and I wanted a Cij element, the rule is this. You take the matrix A, take its Aik element, multiply with Bkj element, and sum over k from 1 to n, where n is the size of the matrix, square matrix. Okay, so it's this 2 by 2 matrix. In this case, k equal to 1 to 2. Is this something you can remember? Okay, it's easy to remember the rule. So Cij equal to Aik into Bkj. Okay, just the usual kind of product when you do with numbers. But you have to do it such that the k comes to be the same, and then you have to do an addition. This is the easy thing to remember. You should know it. Some special matrices. Identity matrix. Identity matrix is the one, it's like the number 1 when we deal with just numbers, not matrices, right? So it has the property, it's defined like this. Identity matrix has all the elements 0 except the diagonal ones. So diagonal are these ones, A11, A22, A33. These are diagonal elements. They are non-zero. Rest are all 0. Okay, this is the diagonal matrix, and since all the diagonal elements are same and equal to 1, this is called identity matrix. What is the meaning of that? It means that if I multiply any matrix with identity matrix, I get A back, right? So when I multiply 2 into 1 is 2, right? So that 1, the role of 1 is played by this matrix. Okay, it's also equal to this. Unlike the numbers where 2 into 3 is same as 3 into 2, it has a name, it's called commutativity property. For matrices in general, that's not true. So A into B is not necessarily equal to B into A. This was a simple example, it was true, but in general, this is not true. Okay, this is a very important thing to keep in mind. Unlike numbers, 2 into 3 is equal to 3 into 2, but matrix A into matrix B is not equal to matrix B into matrix A. Okay? And just like for numbers, so I said identity matrix I was the analog of number 1. Okay? Now we do division when we deal with numbers, right? So the inverse or the reciprocal of 2 is 1 by 2. What's the reciprocal of a matrix? It's called inverse of a matrix. Okay, which has the property that when I multiply A with A inverse, what do you think I should get? Huh? Identity matrix. Okay. Okay, let's learn how to calculate A inverse for a 2 by 2 matrix. So A is that matrix. Let me write it again. How do we calculate A inverse? So you need to do a series of operations. Let me take you through slowly, one by one. So first thing is this. I want to get the 1 element of A inverse. So what you do, imagine in your head, is I go to matrix A, cut these two, get rid of these two. What am I left with? A to 2. So I first write A to 2 here. Okay. To get this element, I repeat the same operation. I imagine deleting these two guys. I'm left with A to 1. And similarly, A12 and A11. The job is not yet over. After that, that's the first step. Then you have to put some signs. This is odd element 1 1. Sorry, this is 1 1, right? So 1 plus 1 is 2. This is even element. So you put a plus here. This is the 1 2 element of A inverse. Put a minus here. Again plus here and a minus here. Okay? We are still not done. This is step 2. First was deletion. Second was putting signs. Third is what is called transpose. Okay? So transpose of this matrix is swapping these two. Okay? That's the third step. And then you have to divide it by a certain number called determinant. So taking inverse of matrix is not that easy. I strongly urge you to please work out few examples if you have forgotten how to do it. Okay? So, but this is the answer for 2 by 2 matrix. Now what is this det A? Det A is the determinant of a matrix. Okay? And for this sec 2 by 2 matrix, it's given by I'm just giving you the answer here, but please work it out or look up any book you like. Okay. Important thing. Okay, let's do example perhaps. How about this matrix? Can you tell me the inverse of this matrix? So we just have to plug in numbers. Tell me the inverse of this matrix. Right? That's the definition of inverse. So A11 is 2, A12 is 4. A21 is 3 and A22 is 6. Definitions are clear, right? Hold on. You have to say no. Other guys, tell me the inverse of this matrix. Huh? This is a funny example, right? Come on, tell me. Determinant is 0. So when I have something upstairs, 3, 4, some number upstairs divided by 0, that's a funny number, right? It's infinity. So if I want A inverse to exist, determinant should be non-zero. So for this one, A inverse does not exist because determinant, so A inverse will exist if determinant of A is non-zero. So you need that A to be non-zero. So the first thing to calculate before you do this operation is to do this operation first, so that you know whether you have to do the other operation at all or not. It should be non-zero. For this one, it's 0. Okay, try this example. 1 0 2 3. Tell me the inverse of this matrix. This plug-in. Does the inverse exist for this matrix? Yeah. Is it determinant? Plug-in numbers. 1. 3, right? This into this minus this into that. Okay, that's a determinant for 2 by 2 matrix. Determinant exists, and again you plug in everything, and then you will get A inverse. One thing, whenever you have an answer, how do you know you have done it correctly? For example, in this case, you plugged in everything. You got an A inverse expression. How do you know it's correct? What will you do to check your answer? Yeah. So once I have done my exercise, I will find A inverse, which in this case turns out to be what you should do is to multiply. I told you how to multiply matrices. Multiply and check that indeed you get 1001 matrix. Okay. Now, so why are we doing all this matrix stuff? It's important because when you will see, when we analyze these models, which we'll learn in the next week, we write down differential equations or recursion equations or difference equations. Okay. And they typically involve such matrices. Okay. And we need to do certain operations in order to find, for example, allele frequency. You will be writing a recursion equation for that. Okay. So hopefully it will be useful there. Okay. So let me first state the problem more clearly. So typically we wind up with such problems. So I have this, let's say, allele frequency. Okay. This is the rate of change of certain quantity, which takes values x1, x2 till xn. Okay. And it's related to itself through a matrix. Okay. So what I have is a set of differential equations. Let's take n equal to 1. Then I have simply this. Right? Suppose n was 1. It was not a vector. It's just a number. dx1 by dt equal to ax1. What's the solution of this differential equation? How do I solve differential equations? We know this is a derivative, right? Right? I want x1. How do I do it? I bring this guy downstairs. Okay? Bring all the x's together, if possible. Okay? And take this guy there. Okay? Then integrate. So here you're using calculus. Okay? Okay? So when you integrate, what's the integral of 1 by x? We just learned log x. And then this is 80, and then you can satisfy yourself that this is the solution of this differential equation. Okay? Okay. But now I have something more complicated. I have a matrix. But suppose matrix was a diagonal matrix. A was a diagonal matrix of this kind. Okay? Then, and is just 2 by 2. So I'll have dx1 by dt equal to lambda 1 x1 and dx2 by dt equal to lambda 2 x2. Okay? So this you need to work out a little bit. You can check this. You plug it in here, do the matrix multiplication. These are 2 equations you will get. But this is easy because we just learned, right? But in general, we will get non-diagonal matrices. That means these elements will also be non-zero. Okay? So that you will get something like A12, X2, and A22, X1. Sorry, A1, A21. This is complicated because if I want to solve for x1, it depends not only on x1, it also depends on x2. Okay? Similarly, if I want to solve for x2, I need to know not just x2, but also x1. Okay? So for these kind of differential equations, what we need to do is, it would be nice if we can reduce the system to something like this. That means we want to diagonalize a matrix. So you will keep hearing, sometimes you hear the word, after diagonalizing the matrix, I did this. Okay, the answers come out when you go to a diagonal basis. So it's important to know how do we diagonalize a matrix. Okay, so I will not go into the theory, I'll just give you an example. So idea is clear, why are we diagonalizing a matrix? Because if I can diagonalize it, I can solve it. Let me illustrate it by an example. Suppose let's take an example, simple example, the previous one, 1023. This is a non-diagonal matrix, right? Because this guy is non-zero. Correct? Okay? Okay. And I want to diagonalize it so that I can reduce it to this form, and therefore I'm possibly done. Okay? So I didn't write it quite correctly. I need to change the, diagonalize the matrix and go back. There are some steps involved, but let me not get into that. let me just show you how do you diagonalize a matrix. Okay, so I have this matrix A. So this is a thing that we need to do. So I want to write it such that it reduces to a form this. That's my goal. Okay, so these are the operations involved. First step is to find what are known as eigenvalues. Eigenvalues are these things. So what you do is to consider a new matrix A minus lambda I. I is the identity matrix. So this is 1 minus lambda, 0, 2, 3 minus lambda. Consider this matrix. Okay, so lambda times the identity matrix and find its determinant and put it equal to 0. Okay, so consider this matrix. There is some reason for it. Let's do it. Okay, and calculate determinant. And we learned how to do determinant in the previous page. So the equation is this. So I want to find lambda. Right? This into this minus this into that. That's the determinant of a 2 by 2 matrix, right? So I want to find lambda. Can you tell me the lambda for this matrix? What is the solution of this equation? Yeah, lambda. So it has two values. Lambda is 1 or 3. In this example, these eigenvalues, lambdas are called eigenvalues. They happen to be different, but that's not always the case. They could be same. Okay, that's a little bit more complicated case. I won't discuss that. Okay, so that was step 1. Then we find what are known as eigenvectors. Okay, so eigenvectors have this property that the matrix, when it acts on this vector E, it gives you that vector back multiplied by these eigenvalues. This is the eigenvalue equation. Okay, so first step was to solve this equation, that determinant of A minus lambda equal to 0. You got the lambdas. Then I want to solve for E vector. Okay, let's do it for this case again. So let's say these are components E1 and E2 equal to lambda times E1 and E2, where lambda is 1 or 3, right? Suppose lambda is 1. I want to find an eigenvector corresponding to eigenvalue lambda equal to 1. Okay? So how do I do that? We learned how to multiply matrices, right? Okay? So can you tell me E1, E2 for eigenvalue 1? Can you solve this equation, please? What's the left-hand side? We know now, right? Tell me the vector. The left-hand side. This into this plus this into this, right? How much is that? That's E1. This into this plus this into this. Okay? And this is 2E1 plus 3E2. Okay? So I want this equal to this guy. And I want to solve E1 into subject to this. So E1 equal to E1 doesn't give me anything. But the other one, okay, E1 equal to minus E2. So I will say that the eigenvector corresponding to eigenvalue lambda equal to 1 is a constant C, some number. Doesn't matter, 1, minus 1, you choose something. C, and the other one must be minus C. Usually we write eigenvectors which are normalized, which means you take a square of this plus square of that, and then take a square root and then divide. So in this case, it would be C square plus minus C square. Okay, and it reduces to 1 by root 2 minus 1 by root 2. Okay, So I'm leaving this as a homework exercise because I think we have less time now. Okay. Yeah. So please work it out yourself for the lambda equal to 3. Is the idea clear? How to diagonalize a matrix? Okay, I have not yet finished. So I just told you how to find the eigenvector corresponding to lambda equal to 1. I'll just give you the answer. So for lambda equal to 1, we'll find the eigenvector to be this, and lambda equal to 3 okay. Okay, so this was step 2. Finally, step 3, you write down a matrix U whose column vectors are these eigenvectors. Okay, just I'm telling you moronically, just mechanically what steps you should do. Okay, so step 3 is this: you write the column vectors as to be this. Then here is the claim. So I'm claiming okay, here's the claim. So let me just focus on this. So I'm claiming that I have that A matrix. I gave you the U matrix. If you multiply, you will get a matrix D, which is a diagonal matrix. It's this matrix. Okay. So then I say that I've diagonalized the matrix by going to a different basis. So okay. There's several steps involved, and you just have to sit down and work it out yourself. Okay, but this is what you have to do: find eigenvalues, find eigenvectors, and form this matrix U. Okay, and then that can be used to solve the differential equations. Okay, if there are more questions, I can go ahead, but otherwise I think I'll just leave it at this. Okay. Okay, so I strongly urge you, please work it out. It just doesn't work if you don't sit down and do it yourself. It's just very hard to learn otherwise. Okay. Okay. Let me do the last part, which is some basic probability theory. So what's the probability of an event? So let's think of a dice or a coin. I flip a coin. Okay. So it will either you will get a head or a tail. So the number of outcomes is 2 of them, right? So when I ask you what's the probability that you get a head, what do you expect? How much is the probability of getting a head? 1 by 2. But when you're saying 1 by 2, you're assuming that your coin is extremely good, for which head is as good as tail. Okay, right? Okay. So in general, it's not true, but I'm pointing out that you have made an assumption in saying half. Okay, but probability of an event is, so when you said, okay, so the definition is this: number of successful events, successes divided by total number of experiments. That's the basic definition. Okay, and S, where NE is very, very large. So you have to do lots of experiments. You can't just flip single coin and tell me, it's half. I mean, then it will be 1 in fact. Okay, so if I do lots of experiments, this object tends to a constant, it's called the probability. That's the definition of probability. Okay? Okay. So I should mention for dice, etc., you said because there are, like for example, dice, there are only 6 possibilities. It's discrete. It takes 6 values. But suppose I ask you, what's the probability of rainfall between a value x, of having a value x? How much would that be? I want a value exactly x of the rainfall. What's the probability of that? It's 0, because x is a real number. So I have to specify 0.1389. I mean, keep going, right? So I don't talk about probability of x, but probability of a value lying between x and x plus dx. So one writes down a distribution, probability distribution for continuous variables. So it's a probability distribution, and the probability therefore is px dx. Probability lies between x and x plus dx. Okay? Okay. Now there are some simple rules that we should know. So let me just write down the answer. Can we have the AC, please? Probability, if I have 2 events, A and B, probability that A occurs or B occurs or both occur is equal to probability that A occurs plus probability B occurs minus probability of both. Okay? And this, again, it's not something mysterious or something that you have to mug up. It's very easy. Let me explain. Suppose I do an experiment and I have 2 outcomes, A and B. And I do this experiment n times. What can happen? Either only A comes any number of times and B doesn't come. A comes, A doesn't come, and B comes n number of times. Both A and B come. Oh, sorry. Okay? Both the events happen, and that number is NAB. None of them happen, and let me ignore the n cross. Okay? So let's calculate the probabilities that I wrote in that expression. So can you tell me probability of A? So I've given you the results of my experiment, right? A happened any times. A, B happened this many times, both, and none of them. Tell me the probability of A using the basic definition of probability. Huh? Yes, please, Laura. NA. Is this so? I mean, everybody agrees with this? Huh? NA plus NA. So it's what probability of A occurring. A happened here, and so it's here. Okay? So what we need to do is to look at the column 1. This is a success, so it's this. We just explain that. What is this quantity? It's this probability of A given that B has occurred. That A happens given B. What does that mean? So I want to look at the cases in which A occurs provided B did. B happens in this case and this case, right? So I will not be dividing, in fact, infinite number of moments, okay? But usually these are 2 things that will encounter. Variance you will hear about. Variance is given by x square average minus x average squared. Okay, that's the definition of variance. And standard deviation is square root of sigma square. Suppose somebody does experiment and tells you, oh look, I did an experiment in which x bar came out to be 4 and x square bar came out to be 3. Would you say, oh wow, great experiment? Or would you say, what nonsense? What should you calculate? Somebody gives you this result from experiment. I will say nonsense, because I'll calculate the variance, which is 9 minus 16 negative. Variance is a positive quantity, because you can write down sigma square. Please, this is as a homework. This can be written as x minus x bar square. So this is equal to this, okay? And then take the average. So I'm summing positive numbers. It has to be positive, right? Okay? So this number has to be greater than square of the mean. Okay, I think I have very less time now. So I'll just tabulate various distributions that you might encounter. The most basic one, binomial distribution. So when we talk about binomial distribution, one automatically thinks of tossing a coin. So if the probability P head comes and Q is the probability of getting a tail, not necessarily equal to half, then the probability of getting n heads in capital N trials, that means you do capital N experiments, that's given by this expression. Whereas this is equal to, it's a binomial coefficient. Okay? And there are two important properties that you must remember. One is this mean, n times p, okay? And the variance, okay? You can show it, but you should just remember this. I should just mention these geometric and exponential distributions, they are related. So geometric distribution is probability of getting n successes with the success probability being p is of this form, and exponential is similar. All you have to do is assume that p is little and n is large. You can make it an exponential, and then let's say here p is the success probability, and here lambda is the success rate. Poisson distribution. So it can be derived from binomial distribution. There are two important things that come out of binomial distribution: Poisson distribution and Gaussian distribution. Poisson distribution comes from binomial distribution. If I take n, let me explain what it means. So what it means is this: suppose I do a numerical experiment. Okay, I toss a coin. I mean, I just do by hand or in a computer. Okay, and I have, let's say, n equal to 100, and the probability that I get a head is 0.1. So I did 100 experiments, and probability of getting a head is 0.1. But if I increase the number of experiments by 10 times and decrease the probability of success by the same amount, such that this product remains a constant, then the binomial distribution will become a Poisson distribution. That's the meaning of this limits. That is, you stretch one guy and reduce the one guy such that the constant, the product remains a constant, such that NP is fixed. So you fix a number. It could be larger than 1, smaller, any number you like. Okay? And this is how Poisson distribution looks. Okay, so this is somewhat different from binomial distribution. Okay, it's a factorial, but this is mu to the power n. An important property of Poisson distribution is mean is mu, right? Because that's what I wrote there for binomial distribution. But variance is also mu. In fact, it has a more stronger property. All something called cumulants are same. So for this, mean and variance both are equal. Then you have a gamma distribution. Okay, so here's some formula for it. Can you plot this function for me for n equal to 1? When n is equal to 1, how does this function look? For n equal to 1, do you see something here? What happens for n equal to 1? It's lambda into e to the minus lambda t, which is the exponential distribution. It's a generalization of exponential distribution. And the reason it's called gamma distribution is simply because you can write this as a gamma function. Okay, so there's some reason for it, but it's a generalization of basically the exponential distribution. How does it look as a function of t for n equal to 1? How does this function look? Does it increase, decrease? Is there a maximum? Is it oscillating? How is it? Exponential function, no? You just did the increasing guy. Now it's decreasing guy because there's a negative sign here, right? Okay. So n equal to 1. Suppose n is larger than 1, then n equal to 2. Let's say n equal to 2. Can you plot this function? It is plotting, please do it. N equal to 2. How does that function look? Right? Can you plot this function, t into e to the power minus lambda t? Can you plot it? How does it look? Is it like this? Then it increases and then decreases, right? Because at t equal to 0, its value is 0. So this function will increase and then decrease. This for n larger than 1. Suppose n is half. Then n less than 1, how does it look? What's the shape of this function? What happens at t equal to 0? It diverges, right? This is constant here. And this is like this. Okay? It's more squeezed. It's more squeezed in this side. Okay. I think I have time left. Okay. Okay, so let me just introduce two more things, which is the covariance and variance we just learned. Let me introduce covariance and correlation coefficient, and then I think I should stop. It's already a lot of words and stuff. So far, so I gave you this table, you know how these look, so that you can sort of look back and reference. But these are all referring to a single variable, x. Suppose now I have two variables, x and y. Two random variables, x and y. So the covariance y is defined as okay. What does this object mean? Xy into bar. What does this mean? X bar we know, right? It's dx, it's x px integral, right? What does this mean? Xy, what does this mean? If I write in a longhand as an integral, this stands for x into y, probability of x and y. It's a joint distribution, integral over x and y. Okay, this is shorthand, but what we mean is this object. Okay, okay, and we learned events are said to be independent if probability of A and B is equal to, for independent events, probability of A and B is equal to, yes, right? So for independent events, P of x into P of y, okay, and therefore this is equal to x bar into y bar for independent events, right? Therefore covariance for independent events will be 0. Okay. So one defines correlation coefficient. So it's just a way of normalizing things. X square, so sigma x square into sigma y square. This is called a correlation coefficient. Okay. So suppose I do two measurements, x and y. Okay, and I'm doing what is called a scatter plot. So on the x-axis, I just plot my data set x and the values for x, and on the y-axis, the y ones. Okay, so how do you think this scatter plot will look if I had if my two variables were independent? So I said if events are independent, then covariance is 0, and therefore R should be 0. Right? Correlation coefficient is 0. But can you tell me how will this data look? Does this represent a data of R equal to 0 type? What does it represent? What kind of data does, if I have this, scatter plot, if I do, what so if I give you this data, what do you think R might be in this case? Huh? 1? Yes? Okay. So positively correlated. When this increases, the other one increases. In fact, it's linear. So if you put y equal to x, okay, if it is a linear dependence, you will get this. You will see a linearly increasing thing. If R is -1, the opposite. If R equal to 0, there's no correlation, right? So this is the value here, another value here, so that on the average, they look. There's no correlation. Okay, so that's how the typical plots will look. Somewhat deviation, so that if you have a lot of data, it's sort of tilted this side or tilted downward side. It will tell you positive or negative correlations. If you don't see any tilt, that will indicate to you R is equal to 0. But actually, what you should do is to calculate this correlation. I think there's much more, but I think I should just stop because this is too much data. Okay, so I think I'll just stop here unless there's some questions.